All right, so let's talk about vector fields. So we're moving up in the book. We're going to be covering 16.1 in Rogowski in this lecture. So vector fields. So what are vector fields? Vector fields are it can be in any number of dimensions. If we're drawing them, we're going to be drawing them in the plane because it's hard to draw. It's already hard to draw in the plane, let alone in 3 dimensions or even more dimensions. What is a vector field? A vector field is an assignment of a vector to each point, and that vector can change as we move from point to point, right? So we have maybe at this, we have x, y, and at this point we have this vector, right? And at this point we have this vector, and maybe at this point we have this vector, right? Maybe at this point we have this vector. Basically, what it is, it's a function. Let's just write it as in the plane. So vector field. So it's supposed to be the vector mark. It is a vector field. It's a function of the position, right? So it really has a couple of components, right? Maybe let me call it f1 and f2, right? So it's really two functions, right? So you could think of it as it's a vector valued function, right? But so a vector field, we're really thinking of these guys being vectors, right? So where does this come up? Well, it could be maybe you have some fluid moving around. Let's just keep it the plane. So maybe we have we're looking at the ocean, right? And we have where is the water? How is the water moving, right? Well, the water is moving. At each point you can say, well, it's going in the current is going in that direction, and with that speed, right? So at each point you have a vector, but at each point it's a different vector, right? It's not always going in the same direction at the same speed, right? So that's one example. It could also be just the gradient of a function is another vector, and maybe it's not at all coming from physics. Maybe it's just in terms of just the mathematics, right? That's an example of a vector field, right? Gradient of if I take let's do something simple, the gradient of x squared plus xy, right? What is it? Well, it's 2x plus y x, right? Well, that's a vector field, right? Not every vector field is going to be gradient of some function. We'll see that coming up later. It's really in terms of physics, the gradients are what are going to be called conservative vector fields. So they're really it's really they're coming from some conservation law, such as conservation of energy or something like that. It could also be force. It could be a force of gravity or maybe electric force. So at each point, force of gravity, right? If we're in space, well, at each point the force of gravity is different. If I'm very far away from any planet, nothing is really pulling me towards anything. But if we're gonna be very close to the Earth, if I jump off the roof of a building, it's gonna gravity is pulling me down quite fast, right? So it's depending on where I am, it's a different force, right? So depending on the position, I get different vector, right? So those are some examples of where vector fields come up. Right now, think about this thing with the drawing of the vector fields. Let's look at a sort of a simple vector field. Let's suppose that it's just yx. It's going to be sort of, well, we're going to see what it does. And let's try to draw it. So if we have, I could actually make it align with my little squares over here. If we, so maybe this is you know, these are the units, right? Now, what I can do is I can do this, right? I could pick a whole bunch of points. Maybe I can pick the points on this grid and try to draw a vector, right? Well, let's try that. So at 0, 0, well, I can just get 0, 0, right? So it's not going anywhere over here. How about over here? This is at the point 1, 0. So I get 0, 1. Well, 0, 1 is precisely this guy. Okay. How about at this point? Well, here we're at 2, 0, and the vector is supposed to be then 0, 2. Okay, that's easy. At this point, similarly, I get 0, 3, and so on, right? I get over here, I get a similar thing. If I'm at minus 1, 0, I get 0, minus 1. Okay, that's easy. Similarly over here, similarly over here. Okay. Let's now do this line, right? So about over here, this is where I'm at 0, 1. So if x is 0, this is 0. 1, this is minus 1. So this is supposed to go in the, so this is minus 1, 0. Okay, good. What about this point? This is the point 1, 1. Well, if I'm at the point 1, 1, and the vector is supposed to be minus 1, 1, right? So it's supposed to go left by 1 unit and up by 1 unit. So I'm getting this. How about this? This is where I'm at the point 2, 1, right? So I will get minus 1, 2. So up by 2, left by 1. How about here? Well, here, you know, similar thing. Up by 3, by 1. What about here? There is where I'm at minus 1, 1. Okay, so I will get at minus 1, 1. I get minus 1, minus 1. So I get go like this. Over here, I'm at minus 2, 1. So I get minus 1, minus 2, and going like this, and so on. I could maybe do a couple more. Over here, I'm gonna get this. Over here, I'm gonna get this. You know, over here, I will get this, and you can see that I haven't even done everything. It's already becoming sort of a nightmare, right? Well, I could have chosen fewer points, but another way that this is done is that we don't really worry about the size too much. We maybe do the size a little bit, but we scale it down so that that these vectors don't really, you know, cover each other. So we would have maybe over here a little bit, and you know, maybe longer here, and then like this, and then like this and like this, and here a little longer and much longer, and then over here we'd go like this. We'd have a little longer here, right? Over here we get this, and so on, right? You sort of get the picture. So that's generally what people would be drawing, right? They'll scale it down so that you can see the overall picture and see a mess of lines. Sometimes people just draw the direction. Sometimes the direction is the thing that's necessary to understand. But it always depends on what the vector field is. What are you trying to get out of it, right? So that's the way that we would at least try to draw these vector fields. Now in 3 dimensions it's going to be even tougher, of course, because we have to draw a whole bunch of arrows in 3 dimensions, and computers are much better at doing this than doing it by hand. But even then, you have to be a little sort of you don't always just give the computer, well, here's a vector field, graph it, because it's not going to graph it in a way that might be useful. It might give you something that doesn't tell you anything. Just like any sort of visualization, it's there's still, computers cannot make the decision of what's the best way to visualize data, right? All right. Now, a couple of maybe points of notation, or terminology. So if we have an f of xy as a unit vector field, that's if I take the size, if I look at the size, if I look at the magnitude of each vector, it's always 1 for all xy, right? So it's a unit if it's of unit length. All the vectors are of unit length. All the vectors are unit vectors. And you could always make any vector field into a unit vector field by just dividing by the magnitude, right? You could take a vector field f and divide it by the size, just like you make unit vectors, right? Except now f and magnitude of f are functions of x and y. Okay. Now could be also f is a radial vector field. That should be an E. If f points towards or away from the origin and depends only on distance to the origin. That really means let me just draw an example. A radial vector field is something that maybe always points out, and if you rotate the paper, the vector field looks the same, right? Or it could go towards. It's really just telling you a radial vector field is something that if you if you know how far you are away from the origin, then that's all that you need to know, right? So, for example, force of gravity. If we have a single planet, let's say, right? There's nothing else in the universe, or maybe everything else is really, really far. So then the force of gravity is really going to be, what that planet does to a small object, right? How does it act? Is really a radial vector field. And you only need to know how far away from the center of the Earth you are, and that tells you everything. It's always going to be pointing towards the center of the Earth, and the closer you are, the faster you're going to fall, right? I mean, the more force is there going to be, right? It's sort of exactly the opposite of this guy, right? And these guys come up quite often. Now, maybe something before we move to the next page. If we have a three-dimensional, right? So over here we just get two-dimensional. In 3 dimensions, well, it's the same thing. It's just that it's a function of x, y, and z, and there are 3 components. And f3, x, y. Okay, I ran out of room over here. All right. Well, for example, maybe x, y, z squared, x. I don't know. Just whatever. 3 different functions. Really, it's a vector valued function of 3 variables, right? So that would be a vector field in 3 dimensions, right? Well, everything is really the same, and still would be the definition of unit or radial vector field would be still the same. It'd just be harder to draw. All right, let's look at so-called conservative vector field, sometimes called potential vector fields, or gradient vector fields. Those are all the same thing. So f is conservative if if f is a gradient of some function f, right? And little f is the potential. You have to be a little careful with physicists, or maybe if you're a physicist, you have to be a little careful with mathematicians, or at least some mathematicians. It's for physicists, usually the potential is minus s, right? Usually physicists write, and I'll write it with a different letter, really they write something like this, which is the same thing as the gradient of minus g, right? So for a physicist, it's minus the gradient of some function, right? And g is the potential. But that's the sort of the same thing. The reason for this is that if you have some force field and it's a conservative vector field, it's a potential vector field, then what the physicists, they want to think about it as the way it's acting is that you're going downhill, right? Because you think, well, if I think of the graph of my potential and I'm a little ball or something, then I'm rolling downhill. I'm going towards the lower potential, right? And so the gradient always points uphill, right? So they go exactly the opposite. They go minus, right? So that's really the only difference. So it's just, physicists don't want to say that everything tends to the highest potential. They want to say it goes to the lowest potential, right? Everyone's minimize potential energy or something. So that's a slight difference. But in terms of the mathematics, all it is putting this negative sign here, right? And this might seem a little nicer somewhere, but actually in some if you're doing physics, just this basic Newtonian physics, if you do this, then you'd have that minus sign would come up somewhere anyway. So it's not like you're really saving. It's just a different convention, right? What is it that we're calling the potential, right? All right. So not every vector field is a conservative vector field. Not every vector field has a potential. It's not a gradient of a function. Now, how do we maybe figure out when this is so? Well, this is when if it were, right, if f was the gradient of f, and let's just look at two variables now, then it would be f sub x, f sub y, right? If it's the gradient of f, right, of this potential. Well, what does that say? That says, well, let's figure out something more that we can do with this. So if we took if I took this component, right, and differentiate it with respect to y, I get f sub xy. Now if I took this component and differentiate it with respect to x, I would get f sub y x. But those are supposed to be equal, right? So so how do we how can we tell if a vector field is conservative and if it has a potential? Well, one way is and this we'll see more of this later, is to basically check the partial derivatives, right? So if I have let's do an example. Let's suppose that I have minus y x, right? So this is when f1 is minus y, f2 is x. So what is this equation really? This was my f1 and this is my f2, right? So this equation is really the y derivative of f1 is supposed to be equal to the x derivative of f2. Okay, so right, let's check this over here. What's the f1 y? Well, this is just minus 1 f2 dx. That's just 1. Okay, minus 1 is not equal to 1, right? So minus yx is not conservative. Definitely not, right? It's there's no way that it could satisfy this this equation, right? Well, let's look at another one. What if I change this just a little bit? What if I make it yx, right? In that case, f1 is then y, and f2 is then x. So in this case, if I do y, this is going to be 1 f2 dx equal to 1. And so, yeah, 1 is equal to 1. Do I know that it's conservative? Well, I don't know. Do I? I mean, this just said that if it was conservative, then this should be true. Does it necessarily say that it is a conservative vector field? You know, that's a trickier question. We'll talk more about that. But let's look at this specific one. It's actually, you know, the answer is essentially yes, but it really depends on where the vector field is defined. If it's defined in a region with a hole, then it's not true. If it's say there are some singularities, it might not be true. It's not necessarily it's not true, but it might not be true. Really, the easiest thing to do is to the one thing that you can definitely try to do is to try to find the what the potential is, right? So now we know we have a shot, right? We think we know what this could be, right? Well, what is this? We're trying to find a function f such that f sub x is y and f sub y is x. Now what we could do is we can try anti-differentiating, except we're anti-differentiating two things, right? So we could start with one of them. So let's anti-differentiate this thing, right? The first f sub x equal to y, right? That should say that f is equal to, well, if I anti-differentiate it to y, I get xy plus some constant, where that constant it's a constant if we're anti-differential with respect to x, right? So it's when y is fixed and x is changing. But for each fixed y, I might get a different different constant, right? And so I know, well, it's something like this. So does this work? Well, I tried. So we do f sub y, and that would be, well, if I differentiate, we get x plus, well, it's just a function of one variable, so I'll just write it as c prime y, and this is supposed to be x. Oh, this says that c prime of y is 0. So it's supposed to be constant, right? So we get that f is actually xy plus c, some constant which does not depend on y, right? And we can, we can just visually check that if I differentiate with respect to x, yeah, that's just y, this is the constant. If I differentiate with respect to y, yeah, I get, sorry. All right. So that's sort of the general procedure. Now it's, you always need to worry about, you need to add this c, because sometime you might what if you had let's do let's suppose let's do another one, right, where this c is actually necessary. So let's do, because here I could have just x y as you know, that's the one over here, but let's make it a bit more fun. Let's suppose that it's this, right? And so we're looking for an f such that f sub x is y and f sub y is x plus 2y. So if we do the same thing and we start with the f sub x and we start anti-differentiating, we get that f again xy plus c of y. But now if you just say, well, I can just ignore the c, I'll try xy, well then the y derivative wouldn't be this right thing, right? Because the y derivative with this f is x plus, sorry, plus, not equals, plus c prime of y. This is supposed to be x plus 2y, right? So we know that c prime of y is supposed to be 2y, and so we could I can solve this, right? You can anti-differentiate, right? So c you know, y squared plus some constant. Let me call it, I don't want to call it c again, but we already have a c, so d, right? So that means that my f is xy plus y squared plus d. Now I don't really have to put in the d, right? That's just a constant if I'm only looking for some you know, some potential. Any potential will do, right? So those are these two examples. Now maybe just a note about this constant. It's in if you, for example, if you know anything about the electricity, right? It's the, you know, what is voltage is the change in potential, and that's really in physics and basically in applications of this stuff. It's really going to be a change in potential that's important, and so change in potential doesn't really care about these constants. So that's why I mean we can actually, you know, once we have some function, we you know, if we have a different function, it might have it would just differ by a constant, right? But if we take a change in potential between 2 points, those constants will always just cancel out. So usually in applications, you're not interested in all the possibilities for the potential. You're just usually interested in one potential. It's going to be the change in potential between 2 points. That's actually important anyway. All right. Well, let's look at an example where we know it didn't work, and just see, you know, what happens then. Well, here we have f sub x is supposed to be minus y, and f sub y is supposed to be x, right? So maybe we'll start doing the same thing. I have f, if I anti-differentiate the first equation, I get minus xy plus some c of y, right? Then I get then I differentiate with respect to y, so I get f sub y. This is going to be minus x plus c prime of y. And I'm supposed to get that this is equal to x. So I have x is equal to minus x plus c prime of y, right? And this has, you know, this c prime of y, that can only be a function of y, right? And here I'm saying, you know, if I put this x on the other side, I'm saying that 2x is a function of y, and it's clearly not, right? Just a little bit. Right. So this cannot work, right? I basically run into, there is no solution, right? I can start anti-differentiating somewhere, and then I cannot solve the other equation, right? So that's something that you can always do to show that something, some vector field is not a potential vector field. Now, just a couple more examples, and let's not do the computations, because it might be complicated. But for example, this if I look at xy and divide by x squared plus y squared, this is the unit radial field. It always points away from the origin, and it always has a unit length, right? And it turns out, and you can double check the potential. This has potential. If I just take the square root, right, which in polar coordinates is just r, right? So if I just take the function r in polar coordinates, I mean, this is also another way of writing this thing as 1 over r times xy, right? That's another way of writing that. So that's one example. Maybe more complicated. It's a radial vector field, right? And you can do this computation if you want to. Just a little bit of calculus. Another example is maybe the force of gravity. As if you have would be something that looks like this. Minus gm. I'll tell you what these constants are. X over r cubed, y over r cubed, z over r cubed, where r is the distance to the origin. R is distance to origin. So with the square root of x squared plus y squared plus z squared, but it would be really nasty to write it here. And the potential is gm over r. Now g, m, and m are just constants. G is just gravitational constant. That really just gives you the right units. This is the f. That's the potential. Little m is the small mass. That's maybe u. Capital M is the big mass. That's maybe the Earth, right? And you're at x, y, z. The Earth, the center of the Earth, is at the origin, right? And then this is the that's the force field. That's the force of gravity, right? And it's a potential vector field. This is the potential function. Now this is called an inverse square vector field. And if you first stare at it, what the hell? It's over here. There's just 1 over r. Here there's 1 over r cubed. Where is the inverse square? And the thing is that there's an r in the numerator over here that's sort of hiding. If you compute the size, the magnitude of these, you will actually get if I'm doing this correctly, but just copying. It's just some constant, and then I'm gonna get 1 over r squared, right? There's really over here, if you ignore the constants, right, then you get this x, y, z. Well, that has size r, right? That's that has really this size, right? So if I'm dividing by r cubed, well, then I really have something like 1 over r squared, right? And times the whatever the constant is. It's not relevant to this. How does it change? So it changes as 1 over r squared, right? As so your the force of gravity goes down by square of the distance as you move away from the Earth, right? Now, finally, before we end for today, the thing about how do we tell conservative vector fields? What do they satisfy? Well, we can we have the following. So we have there are 3 components. Everything is a function of x, y, and z, and this is supposed to be, if it's if it is a gradient vector field, right? It should be f sub x, f sub y, f sub z, right? Well, now we get if I take all the mixed derivatives, well, there's more mixed derivatives that I can do. I can do the same one as before. X y is supposed to be f y x, right? But there's also f sub x z is supposed to be f sub z x, and there's f sub y z is supposed to be f sub z y, right? What does that mean? Well, that means, one of them is the same as before. If this is f sub x, I take the y derivative, right? Well, that's supposed to be the x derivative of the second guy, right? Now, similarly over here, if I take the z derivative of this, then this is the same thing as if I take the x derivative of the last one, right? And finally, I could take the second one, take the z derivative, and that's the same thing as if I take the last component and take the y derivative, right? So these are, so in 3 dimensions we have three equations that we need to satisfy, and as I said, a lot of the times, at least sort of nearby a point, it's going to be good enough for finding a potential. Now, finding the potential requires integration. It's exactly that the thing that we looked at before. You have to sort of integrate in one variable and then differentiate and see if it works. Well, here you would in 3 variables you would have to do this a couple of times, because f sub x, so maybe you anti-differentiate in x, right? Then you differentiate with respect to y, right? And get something. Your constant would be now dependent on y and z, and we'll do an example of this next time. And it's then you anti-differentiate with respect to y, and you differentiate with respect to z. So you have to do this 2 times. It's it has to you have to make sure that you get all 3 of these, right? Before we only had to make sure that we had all 2. So anti-differentiate, right? 1 differentiate and see if it matches up. So now you'd have to do a little bit more, but it's sort of the same idea. Okay, so we'll talk more about vector fields next time for in chapter 16. All right.